Share the screen. All right. So let's get started. This is the, one of our last topics, basically. We started with regression. Then we moved to classification, multi-layer perceptrons along the way via regression and also classification. We did, then after multi-layer perceptrons, we did deep neural networks, then CNNs, right? Then we did GANs, right, for the binary classifier, binary generator, basically. And now we are at the last topic, which is the transformer, okay? So this should be the most exciting thing to you because this is the state of the art. And so that's what we're going to cover today. So you could argue that it took all semester just so that you could be ready to begin to understand the transformer because it's very object-oriented, kind of Joey, his heads thing that he's doing there. It's good. That's kind of the transformer has things like that. It's a very complex architecture, so I'll do my best to explain it to you. All right. So here we are. I'm recording, I believe. So hopefully check, make sure it's recording. The Jupyter notebook that I'm using, I've already posted on the PyTorch repo. You can just go to deep learning and go to transformers here and under GPTs. So you can click on that. And then basically there's some information here about the output that I'll talk about. And there's actually, this is the Jupyter basically, so you can click on that. And I will also be running it in the local machine. Okay, I've added this. These are my notes, and I've updated these a little bit. I'm using the matrix multiplications as well as the very object-oriented approach. So it's all in PyTorch, of course. When I did this originally, it was during TensorFlow 1's era. So the matrix multiplications are in TensorFlow 1, but it's basically the math is there. I haven't had time to convert that to NumPy or Torch tensors. So in the future, I will be doing that. But it should be very helpful, I think. All right, so I'll go over GPT today, basically. So I'll start with a little bit of how you run it. So this is just some information. So first of all, there's transformers, right? And then there's GPTs, right? So actually transformers are made up of two parts, something called an encoder and something called a decoder. When you use the transformer with the encoder and the decoder, it's basically called the encoder decoder with multi-head attention deep learning architecture. And it's basically used for tasks like language translation, where you're going from one language to another. However, you don't really just need it for language translation, although the original paper was for that. And it's rumored that even the creators of this didn't really know how good it was going to be. So people divided the parts and started just playing with the encoder or just a decoder. So whenever you're using just the encoder part of a transformer, that's where you get the Berts, Roberta, Albert, all of those BERT models are encoder only part of the transformer. GPTs are the decoder part of the transformer. When I first started to try to understand transformers, I started with the paper, the original paper, Attention is All You Need by Vaswani, 2017, which was for language translation. I had to understand the encoder, the decoder, their whole interaction. It's tough to understand it like that. I have come now to, and really, ChatGPT, for instance, I want to stress, which is really the state of the art right now, is a GPT. So it's a decoder only. It's not the full transformer. It's only the decoder. So actually, that very nice large language model, right, is only the decoder. So if we can get rid of the encoder and just focus on the decoder, that's a good thing. Because the encoder and the decoder are actually very similar. They're not really that different. And so I do think it's much better to try to understand transformers by just focusing on either the encoder or the decoder part. And if you're going to pick the two, we'll pick the most exciting one, which is the decoder. All right, so that's what I'm going to do. I'm only going to focus on the decoder part of the architecture, which is what gives rise to the GPTs, okay? GPT just stands for Generative Pre-trained Transformers, okay? So this is a tiny ChatGPT style LLM. It took me to train it about 20 minutes on my GPU. So if you decide to run this and you only have a CPU, you're going to have to leave it overnight probably. The data is here. It's this file, input.txt. You can download it from the GitHub, and it's from Shakespeare. So this is a tiny Shakespeare. All it does is it speaks a little bit like Shakespeare. You could give it Star Wars, Rick and Morty, you know, whatever you want to give it that you find interesting, and it'll start trying to speak in that manner, okay? All right, so let's go back. I have some images here that go with the Jupyter, so I'll cover those in a sec, but I want to give you some basics of it. The tokens are really important in the transformer. So there's actually, you can think of it as two passes, okay? There's one pass where you give it all the data, and it needs to figure out what are the most common words in there. Now, transformers don't actually use the words. Instead, they use like the equivalent of the syllables, but they're not syllables. You can think of it that way, and they're called subwords. So those are calculated through some algorithm called sentence piece that gives you frequency. However, that would give you a vocabulary that's really large, hundreds of thousands of tokens. For this example, just to keep it very simple, because it's just one small file. First of all, I'm not, you know, the amount of data that Llama and ChatGPT get is basically, you can almost say it's the whole internet, all the books in the world. You know, that's a lot of data, right? It takes months, takes 10,000 GPUs in the cloud, highly specialized GPUs, and it costs millions of dollars. Funny story, OpenAI got $10 billion from Microsoft, right, as an investment. But that money goes directly back to Microsoft because the majority of the money is cloud computing, and Azure is Microsoft. So they're really like, yeah, here's the money, and then pay it back to us to use our cloud. And so it's a kind of a nice deal. But anyway, so that's very important. Now, the alphabet for this one, just to keep it super simple, is only going to be 65 letters, okay? So basically, letters and a few symbols from this Shakespeare. You can see the letters literally printed out here, uppercase letters, lowercase letters. Those are going to be the tokens, although, as I said, you would use the equivalent of syllables using some technique. But I'm trying to simplify a lot of things so that you can really, you know, get at the heart of this. So as I said, you would do two passes. One pass is to get the vocabulary. The second pass, then once you have the vocabulary, is to train the actual architecture of the transformer. The approach I'm going to take is very similar to all the approaches we've done. You know, but I will say that the jump from CNNs to transformers is much of a bigger jump than, say, the jump from deep learning was to CNNs. There's just way more going on. All right. So that's why I've given you a lot of the matrix multiplications in there so that you can see exactly what's going on as notes, not as part of the code. The code is in more succinct. This is the, if you decide to train it with this file, so you would have to train this Jupyter on this file, right? These are just some images I provided that are in the Jupyter. This is gonna, the expected training that you're gonna have, the losses, okay? So the losses that you will have, and then basically this is actually the GPT speaking. So this is generated text. So as you can see, if you look at it, it's not perfect because obviously it's not a lot, but come brother with myself and now, right? So it does sound like Shakespeare, like that style. Let thy lord, so you know, but at the same time, for sell, I think it made up that word, honestly. So I don't know, maybe it's a real word. But anyway, this is a generative model. Generative models generate text one token at a time. Okay, that's the idea. Any questions? All right, so let's get started. Let's take a look now at the, I'm going to give you some basics of this. And then we're just going to start running the code, okay? And to make sense of a lot of things. I have so you can read through this. I won't read through all the details here. The original paper by Vaswani et al. 2017, it was done at Google. They shared this amazing thing. OpenAI has become a little bit more like restrictive with things. They don't seem to want to release things that often. But the original paper was released by Google. This is the actual architecture of a transformer, the full transformer from 2017. Okay, so you can see here, this is the encoder part, and the red, where you see the red arrow, this is the decoder part. So if you look, there's an input here, and there's an input here. This input goes through basically all the layers of this to produce an encoded output. And this encoded output becomes an input to all the layers here, but you also have an input here. So a good example, this is for, when they did this, was for language translation. They gave the example in the paper of English and Portuguese. So they were translating from one to the other. So they would give here an English sentence. The English sentence would go through all these layers to produce the encoded version of that English sentence, and that became the input to all the layers of the decoder. And down here, you would give it the Portuguese sentence, okay? Then the Portuguese sentence would go in, plus the encoded English sentence, and all of that was used to produce the next Portuguese sentence, or word, sorry, Portuguese word. So you're translating from English to Portuguese, okay? Now, that's a lot going on there. We are only going to focus on this part, this. So imagine that this whole thing is not there, the encoder. So, and we're not going to be translating, so it's all going to be English. It's going to be, in fact, that Shakespeare text that I just showed you. That's what we're going to give it. Okay, so the language is English. We give it English here, we're going to get English here. Okay, that's basically how it's going to work. So one nice thing about transformers that I really like is the fact that the inputs and the outputs are always consistent. What I mean by that is it's a tensor. It's a three-dimensional tensor that goes in, and you get a tensor of the same size coming out. And then that's the input to the next layer, and so on until you get to the last part. So that's why it's really important when you think of transformers to think in terms of tensors. The dimensions are the thing that are going to help you to understand what's going on. Okay? So let's take a look over here. So remember, we're only doing the decoder. So we're going to get a sentence here. Initially, it's n by 40. Now, the way that I've done this in my Jupyter, so my example initially was n by 40 by 512. The code that I have is n by 256 by 384. So just make a note of that, okay? I haven't had time, unfortunately, to change this in the document, but just make a note of that, okay? So I can't change this graph so easily, and I wasn't able to change it to the actual dimensions in the PyTorch code. So, but anyway, and I think you guys are smart, you can figure it out. So we started with n by 40. N is what? N is, as usual, the batch size. So instead of giving it one sentence, we can give it 16 sentences, a batch of 32, a batch of 64. 40 is the number of tokens that we allow. So that's the equivalent of saying, what is the average sentence size that I'm going to accept in there? Except that, remember, we're not using words, we're using subwords. Now, in this example, we are actually using just letters, okay? But 40 is, so if I have the cat is sleeping, right, that goes in, that's less than 40, let's say, even if you break it out into subwords. So really what happens is the remaining part is just going to be padded, but the vector has to be of size 40. Why? Because we're doing matrix multiplication. So this is an example of code and algorithms having to conform to the hardware that we have available, NVIDIA GPUs in this case, right? So this is why it was done like this. Now, if we have a sentence that's really long and goes over 40 in this example, then we would just truncate it. So that's why you need to pick a size that for most of your sentences will be good. Because what's the problem? If we make that value 400, then we have a much bigger matrix, then we have performance issues, we have RAM issues, we have longer training time, etc. Does that make sense?
So like 50 or 20 better?
Well, nowadays, actually, the code that you're going to use is 256.
Okay.
So it's just in my diagram. I think the original paper of Aswani was 40, I want to say. I can't remember, honestly. But obviously, that was 2017. It's been 6 years, so there's a little bit more computing power. Okay? So, but yeah, it was 40. I think with this one, I kept very much to that. All right, now that becomes n by 40 by 512. So we go from a grid to a cube, okay? So now each word will be converted. So each syllable is an ID. It's an integer. I'll show you that when I run the code very soon. But we can't just give IDs 17, 3, 50 to the transformer. What do we usually give deep learning? We give it vectors, right? We give it 28 by 28, which we spaghettify into 784. You know, we give it little vectors of data. So what we have to do is every word is going to be represented in this example by a vector of size 512. Do you see that? So if I was talking about the cat is sleeping, and those were the tokens, and the is ID 17, but that ID 17 is actually represented by a vector of size 512. Analogous to MNIST being an image of size 784 when you spaghettify it, here we would have a vector of 512. So you might ask yourself, so what are those values that go in? How do we know, what do we put in all those 512 cells, right, that represent da or car or whatever? So the amazing thing about this is that the transformer learns those values. So just there's a similar analogy there to the CNN, where the filter, so the CNN, we just specify the 3 by 3, but there's no values there. And then we just give it training data and it learns it. Similar idea. So we just define the architecture of these embeddings. So in this example, the embedding is 512, but in the code, the embedding is 384. So it's actually a little bit smaller. Okay, so just keep that in mind. Make a note of it, because those are little differences that I haven't had time to adjust. Okay, got it? All right, so so obviously all these changes are happening through the neural network. I have to show you that in the code, but kind of right now I'm just giving you the big picture, okay? Then that n by 40 by 512 goes into these layers. So this orange part is the actual decoder, okay? Which is made up of 1, 2, 3, 4, 5, 6 identical layers called decoder layers, okay? And I have a little graph of that, but they're basically just the input goes in, there's a layer inside that's a new layer called the attention layer. I'll talk about that one. And then after that, it's a feed-forward layer, the standard layer that you guys already know how to use. So again, another analogy to this is that instead of putting in that convolutional layer, we put an attention layer, okay? And that attention layer then is followed by a feed-forward. And we do that 6 times in a sequence. So it goes, so X goes in here, then this is H1, then H1 goes in here, and then it's H2, and so on until we get to the last part. And then notice I have a final linear layer. And a final linear layer is just a standard layer that we've done all semester, right? But this one is crucial because if you notice, all throughout the inputs and outputs of these layers have always been n by 40 by 512. But we need to predict the word in the last one, right? So if you notice, we need to do a transformation there so that our tensor now becomes, instead of n by 40 by 512, it is n by 40 by vocabulary size. Why? Because that's going to be the vector of, let's say that our vocabulary is 70,000, right? That's 70,000 possible words that we can pick from. So the last layer is we need to predict a vector of 70,000 with probabilities, with softmax through them, so that we know the highest, the one that has the highest probability, let's say that's ID 63, then we know what token to select. It's going to be this token that has the ID 73. Does that make sense? So the last vector there is the vocabulary vector. So in my example of the tiny Shakespeare, it's going to be actually 65 possible letters because that was the alphabet that I had. And that's it. That's exactly what happens. Now, keep in mind, there's two final things to think about. The GPTs are what are called autoregressive models, which means that an output of it becomes an input somewhere else. It's autoregressive. That is this little blue line that you see. So the output comes in and goes back in here. So this is a trick that changes whether we're training or testing, right? So if we are training, we don't do that. If we are testing, we do that. So let's think of how this would work. Let's say that the model is already trained. So then we have to give it something. So usually it's a start of sentence token. Like, let's just say, I don't know, start a sentence. That's a symbol that we need to put in the vocabulary. Once we do that, that input goes into the network and it's going to predict the next word. So probably the. Let's just say it. Even though we're going to be using letters, it's more intuitive to think of words. So it predicts the, and that the now is regressed back and concatenated to the original symbol so that we have start of symbol, the. And that goes in through the architecture. And what does it predict? Cat. So now you have cat, that cat goes back. And so now we have start of symbol, the cat goes in again. What's it likely to say? A verb or something, right? So the cat is dancing. There you go. And it just keeps doing that until it's satisfied that it said the cat is sleeping and dancing and then ate some food, and that's it. It just feels like, oh yeah, that's a good enough sentence. Do you guys see that? That's testing. Training doesn't have to be like that because that's actually a bad way of training a model. Why? Because we don't want to train a model with its own predictions. If it starts to make mistakes, that would go back into the training and just cause problems. Instead, you always want to give it the actual true data during training. That's called teacher forcing. So the trick is actually like a brilliant trick. What they did, and it's so simple, they take a sentence and that they use the same sentence for input and output. So whenever we train a neural network, right? We have X and Y, the pair that goes together all the time, right? So we give it an X, gives a prediction. We compare that prediction to the real. That's it, right? We do the same here. But the X and Y here are basically the exact same sentence, except for one minor difference. They are shifted. Remember that NumPy shifting problem you had to do at the beginning of the semester? Exactly that. We shift the word. Why? Because down here, we want to give it the cat is, and up there, we want to, at the output, we want to give it cat is sleeping. So we want to give it the cat is and predict sleeping, and then be able to compare it to the actual word, which would be up here. So we always have the next word shifted over there, but they're basically the two same sentences. Does that make sense, guys? Okay, perfect. So we're almost ready to get into the code. So this is the Jupyter. You can read through it. I've said most of these things. Here are the main ideas. So one thing I've mentioned already is the padding, right? So this is an example. You can see the zeros just are the padding so that it has a size of 40, okay? Masks is a thing that I'm going to skip right now because the mask will make this a little bit more complicated, but you can read through that, but I will just say that the mask is also a trick because of the GPU. What we want to do is we don't want to show it all the information. You did this also at the beginning of the semester when you did that NumPy example of taking a matrix and multiplying it times a mask. You remember that? And then we got all the values below the diagonal. That's what's happening. By multiplying with these special masks, you can hide away certain things from the batch. Okay, you can like the cat, and with a mask, exclude the other stuff because you can turn it into a 0. Even though the data is there, the mask just helps you when you're making the matrix multiplications to make things disappear as you need to. Okay, so that's basically it. The attention mechanism I will discuss. That's really the magic, if you will. I mean, there's a lot of magical things here, but the attention definitely is the mechanism that's extremely important. So I will hold off on that one towards the end. Okay, got it? So the other thing I will mention before we start running the code, I have another graph somewhere in here, I think. Oh, there it is. So this square here is actually just one of the 6 decoder layers that I showed you. Okay, so if I was to zoom in each of those decoder layers in the decoder, this is what they look like. If you notice, the input is n by 40 by 512. The output is n by 40 by 512. Very consistent, right? But inside we have this, which are just neural network multiplications, okay? You have the multi-head attention layer, where this is what Joey was getting at, trying to implement the heads, right? And that's where the attention mechanism is. So we'll talk about that. And once you run this through this, the output is an n by 40 by 512, and that just goes through a fully connected layer to produce an n by 40 by 512. Okay, all right. So that's kind of the overview of it in the Jupyter. Now we are ready to start running the code and start to get a feel for how this works. Okay, so to do that, I think I already have this running. I believe this is, yep. So, okay, nothing's running. So I'm going to run the GPT. It says Tiny GPT or Shakespeare GPT. Okay, so here, all right. So, yeah, I already have output. So I'm going to clear the kernel. I will not be able to run this all the way to the end in real time because this is not my GPU. This would take hours. As I said, but it runs nicely. So just compare it to what's in the GitHub. Run it overnight though on your CPU. If you have a GPU, like some of you that have, 20 minutes. So actually give it more text, and you can give it more text, a bigger file. It's going to be better. It's definitely going to be better. All right, so we are ready to run it. So I'm going to run over here, and then I'll be explaining all the different parts. Okay, so the libraries, I want to demystify GPTs, right? This is like the most bare bones code. You can thank Andrei Karpathy for this code. It's like the most simple GPT I've ever seen of all the transformers. Very nicely implemented in PyTorch. Notice it's Torch, NumPy, tick token is actually that one, or sentence piece are the libraries that you could use to figure out the vocabulary. Like if you wanted to do this properly, you would just do one of these libraries, but I've just skipped it and we're just doing the letters. Also in the book, in the PDF that I showed you at some point in the semester, I did it just manually. So you can actually try to do it manually if you would like. But as you can see, the libraries are exactly the same libraries we've always used. There's the installation function for tip token. Notice that it requires Python 3.9. So that might be an issue. I think if you use sentence piece, 3.7 should work. All right, so let's look at these. Notice that this has way more variables now and inputs. Just to make it consistent, okay, with my graph, the block size was 40. Okay, so I want to stress, this is where that is 40 in the graph. Here it's 256. Also, where I do the math examples, I'm still doing them consistent with my graph because I took this just from the book. And so just be aware, right? I'm mapping these things out. Block size for this code will be 256, but it's equivalent to having the 40. So it's the number of words in the sentence that we're going to allow. Okay,
Is it always gonna be 256?
You can change it to whatever you want.
Notice the model, like, let's say. Would it make a run-on sentence? Or,
They're all sentences vary in length, right?
yes,
But for the transformer, you have to pick one size for everyone. They cannot change. So instead, what you do is if they're greater than 40, you truncate them. If they're smaller than 40, you pad it as I showed.
I see.
So it can be 2256, 40, whatever it is. It's just, you just pick it.
Oh,
Think of it as you make a cube and that cube is what you use throughout. Okay. All right. The batch size is 64. The maximum number of iterations is 5,000. So that's how long you train it. The eval iteration is 500. So that's when you record losses. Every 500, you're recording losses. The learning rate is this number, which should be like 3 zeros and a 3, right? This, of course, you guys that use CUDA, this should be familiar to you. So if CUDA is present, it'll select it. Otherwise, it'll use CPU. Okay. Vocab size, notice it's 65. It's kind of because it's the number of letters. However, if you were using sentence piece or something like it would be much larger because it's not even all the words. It's like syllables, right? Because remember, there's for happy, right? There's happiness, happier, happiest, happily. So the idea is that if you pick syllables, it might learn how to vary hap with all those conjugations, right? But what if you have a new word that you've never seen? You can still conjugate, right? So that's the idea, okay? And embedding 384, that's the 512 in my graph, okay? So sorry about this. I know I just didn't have time to fix it. All right, but that's the 512 in the diagram. Number of heads is 6, all right? So it's gonna have 6 attention heads. What that means is that it's gonna pay attention with the attention mechanism to the same input 6 different times independent of each other, right? And then it just like combines them later. And then the number of layers 6, that should be self-explanatory. That's the number of decoder layers. Okay, got it? So that's 6 layers. Dropout, you guys have played with dropout and you've seen that it's useful to cut some of the connections probabilistically speaking. Okay, all right. So that's the parameter. So I'm going to run that. Now, this is the file. I already downloaded that file. You can get it there from Karpathy's GitHub. It's called input. I'm just going to read it in. And this is really important because I really want you to see this part, right, Neil? The inputs and the outputs to the architecture are really important that they should be clear. The length of the data or the number of characters, we can print that out. As you can see, there's 1,115,394 letters in that. That's tiny, okay? All right, now I'm gonna use set and list just to kind of give you a list of the letters. You can see them right there. So they're just basically, this is coming from that Shakespeare play. Okay, now we can calculate the vocabulary size. I already knew it was 65, but there it is. Okay, that is the vocabulary. Each one of those letters, you can think of it as a token that is going to be represented by a vector of size 384, which should relate to the graph as 512. Okay. Questions about this so far? All right, so we've done this part. Now we can print the number of characters, 65. You can see that coincides. Now, tokenizer. So as I said, there's 2 passes to a GPT. First, you do the tokenizer, calculate the vocabulary, then you do the second pass where you now train the architecture, okay? So this is usually referred to as the tokenizer. All right. So this is a trick that you do in natural language processing. We're using a dictionary, as you can see. Dictionaries are hash tables in Python, which makes them really fast at retrieval. So instead of always like, we need to create a mapping between the letters and an ID, which the ID will just be an integer. So basically, we're creating a dictionary of integer to string. and the reverse of that string to integer, but they're literally the same thing, only reverse. The key is now one or the other. Okay, so you can see here, we go into chars, which we got over here, right? We got it over there, and we enumerate in a list comprehension. So for I, comma, ch, and enumerate chars, and we get the I and the ch, but notice that we're creating two dictionaries, stoi and itos, and where, you know, ch colon I or I colon ch. So basically we're just changing them. This is, so it's the dictionary and the reverse dictionary. So I print stoi, and there you can see letters to numbers. I print the other one, numbers to letters, but it's they map because they were generated at the same time. Okay. Yeah, so this is the dictionaries. Now we need to create these functions. Now here so a transformer is made of an encoder and a decoder, but you also have another encoder and decoder, which are for the tokenizer. Okay, so this is nothing to do with neural networks. It's just we need a way to take letters and convert them to integers. And then once we have the integers, we want the letters back so we can actually generate the text, right? So this is also called encode and decode. Just please don't confuse it with encoder layers and decoder layers, two totally separate things. We're still in the first pass here. All right, so how do I do this encode? Here we can use lambda. Lambda operations are just a fancy way of expressing a function. We're gonna give it an input. So in this case, S, which is gonna be our string, you know, happy, happier, whatever it is. And notice that all we do is in the list comprehension, we grab all the letters for C and S, and we run the S's into the stoi dictionary. And what is that going to give me? Well, I'm giving it a character is going to give me the equivalent integer. So right there, I have my encoder for the tokenizer. So let's go ahead and try that. I'm going to use the sheep language, right? I run the word, and boom, I've got my integer representation. Okay, so now B is 40, A is 39, H is 46, and is repeated twice. Got it? The decoder is the same idea, lambda operation. It receives an input, which in this case should be a list of integers. We iterate, and each one of those goes into the reverse dictionary, and we're going to get the letters back. So I'm going to do that also. Decode, and there it is. Bah. Got it? So we've completed the encoder and the decoder. All right, and then now we're going to proceed to encode the entire play of Shakespeare with our encode function. So notice that's what I have here in the word text. So the text is the whole data, right? And we're going to encode it. And notice we also convert it into a torch tensor, very much like you guys have done all semester. All right, it's done, now printed. And you can see now all the letters have been converted into integers. This is what we're going to use to train our transformer. All right, we are going to split our data into train set and test set, as we've always done. We calculate the size of the data, and we multiply it times 0.9. We got n, and now I'm just going to do slicing, right? Something that you're very familiar with, to create the train data and the val data. Okay, and that's it, done. All right, so these functions here that I'm going to run are not really part of the transformer. Instead, I'm breaking them up so that you can see it step by step. Then there should be a function that has all of it together, okay? But let's think about what I'm going to do. I'm also reducing the batch size and the block size here, just so that we can view it. Because, yeah. It's a train set and test set. 90% for training and 10% for tests. Got it? Yeah. All right, so function to create batches. As I said, I'm just breaking this up because this is really important, okay? So if you notice, sentences are selected here for X and Y. So the input and the output, right? As usual, X and Y, input and output. They're the same sentence, just shifted by one. Where they are the same, but Y is shifted by one from X. So I also, for this example, just to visualize it, I have made the batch size 4 and the block size 16 instead of 256. So it's a little bit smaller. So what am I going to do here? Here, I want to generate 4 integers from my text. What I mean by that is I want, imagine the whole Shakespeare play from beginning to end, right? And every letter in there has a number in sequence, right? I want to just grab one in the middle. So that's if I have 10,000 and I want to get a letter in the middle, that's like 5,000. So I grab 5,000. Then I want one at 25%, so that would be 2,500. And then I want one at like 75%, so that would be what, 7,500. And I have 3 letters that are almost like at a quarter, at the middle, and at 3/4. Do you see that? That's what I'm picking. Because I'm randomly picking starting points of sentences that I'm going to slice out of the text. Do you see that? So let's go ahead and do that. There they are. I have picked these 4 values randomly. And these are positions in my, if you remember, we had 1,100,000 something characters in there. So I want to grab, let's say, character 874,116. I'm starting at that point, and I'm going to scoop the 16 following letters, and that's my chunk for training. Okay? So you can see what I'm doing here. I'm going to iterate in this for loop. And now data is what contains all these letters. I am going to grab these 4 indices, and I'm going to get the actual letter that's there at that index. So you can see I grab 1, 1, 4, 3, and 47. Why is 1 repeated? Because it could be that appears at 231,000 and also at 760,000. Just so happens that I grab the same letter. Do you see that? This is the position of the letter. This is the actual letter in the dictionary. Okay? And now, here comes the nice thing. All I'm doing is, now notice, I'm in data, right? So I'm going to select here I have the data itself, and I'm just going to slice out of that data these indices. Okay? So for X and Y, so I'm going to iterate. In IX, I have 4 indices, correct? I have 4 indices in IX. So I grab the first index, 231,000 something, right? So that then is that value, right? And then what am I doing here? So I'm going to slice from I to I plus temp block size. So I'm slicing basically from, let's say, let's not use 231,000. Let's say 231, right? So I'm slicing from 231 all the way to 231 plus 16. You guys see that? Because that is the value that I define here, 16. Got it? And I'm slicing that. That's X. The Y then should be the exact same thing, but just shifted by 1 to the right. Well, we accomplish that easily. All we have to do is, if this is I, then this is I plus 1. It's shifted by 1. And here also, if we start at I, let's just start at I plus 1, we have shifted by 1. Do you guys see that? And we've got our X and our Y as integers. All right, so let's go ahead and run this one. And as you can see, we got the tensor for X, the tensor for Y. 4 means 4 in the batch, right? 4 sentences. So we're giving it a batch of 4 for training and a batch of 4 for testing. And they're the same exact sentence except shifted by 1. Notice this one is 128, 50, 39. This one is 28, 50, 39. This one ends in 1, 57, 46. This one ends in 56, 46, 39. There is the new word that the model needs to predict. You guys see that? Let's do this one more time. For the last one, 47, 45, 46. Here, 45, 46, 58. Shifted by 1. The last sentence, 56, 59, 57. Over here, 56, 59, 57. Shifted by 1. 58 is what the GPT needs to learn to predict. Got it? All right, perfect. So that's basically it. So I grabbed one of these as an example. And so now, is that actually they've changed, I think. So let me grab another one. Okay. And as you can see, it is a sentence. Place, there, something. All right. That's actually from the real data. Okay. And so that's how you can train. You can just grab randomly sentences shifted by one. That's your X and Y. Do this for the entire internet, all the books in the world. You have a GPT, not Chat GPT, a GPT. Remember that it can't answer questions, but it can start rambling and hallucinating and making stuff up because that's what it can do. All right. So now all of that I just explained, right, is put together in one function, okay? So you can see it's exactly the same thing I just described, but now how this function is what we're actually going to use, okay? So go ahead and run the batch. So I won't explain that because that's exactly the same thing that we did before. Okay, at this point, then, I'm going to start going kind of from the higher level and then working our way into the architecture, okay? You got to remember that picture of how we had an input, n by 40 by 512. That goes into the decoder, which is 6 decoding layers, a final linear layer to predict the word that we want to predict, right? Remember that picture. So we'll come back to this one. This is not so important as this is just a loss function. So that should be very familiar to you, but we'll come back to it. And instead, let's focus on the architecture, okay? So the architecture is made up of several objects that are pulled together one after the other, okay? So we've got the head of self-attention. So notice that when I do this, this is where I have the math, basically, okay? But it's just an example of how the math actually works in the underlying framework because we don't write code like this anymore. This was TensorFlow 1 back in the day, and we don't do that anymore. All right, so this is the actual function head, okay? So this is actually going really deep into the network. So I'm not going to start at head. I'm going to start at the top, and then we need to work our way into this section. What I want to point out is that this is where the attention mechanism is. Notice, though, it's exactly how we've coded things before. We've got our init function where we define things, and then we have our forward function where we do the architecture, okay? But I will come back to this one, okay? This is a head. We're going to have to instantiate 6 or 8 of these heads, okay? At some point. I already covered this. Then over here, and I'll come back to these math operations, which are critical to understand. Then here we have the multi-head attention. So this class is basically, think of it as an encapsulation of the 6 or 8 heads. The 6 heads is what we're using. So the 6 heads that we're using are going in here. So we create the multi-head attention, and the multi-head attention invokes the 6 heads. Where is that happening? Right here. If you notice, if you look here, what is that? It's a list comprehension of a for loop that says for I in num heads. So for 6 heads, create this, which is basically the instantiation of each of the heads in the other class that we defined. And now we've got 6 heads. Do you guys see that? It's a list of 6 heads. It's a for loop, but we instantiate the heads, okay? All right. So again, I need to come back to this because this is, it's kind of like I'm going out, zooming out almost, right? So this is multi-head attention, which contains heads over here, where each one of these has the attention mechanism, okay? We're going to scroll down. So that's multi-head. Then we've got what should make you really comfortable and happy, a feed-forward layer. This one you should be an expert on, right? We've done this all semester. So that's the feed-forward layer that goes at the end after the 6 decoder layers, okay? This one, I shouldn't even need to explain this one, but I'll come back to it as well. But you should be able to make a lot of sense of it. Then we've got block, and block is going to be where you have multi-head attention and feed forward. So you see how this one takes the multi-head, which contains the heads, and then the feed forward to create a block, one block, right? Which block? This one. Multi-head and fully connected. That's one block, okay? We'll come back to it in a second, all right? And then multi-head attention, feed forward, blocks. And then over here, we've got this class bigram language model, which brings everything together. Basically, it actually has our init function, our forward function, which should be very familiar to you, and it's got even our generate function. And the generate function is what you're going to use when you're generating text, because it's going to invoke forward. So really then, this is where we need to start, like, to zoom into all the parts. So I just want to show you that after that, we just instantiate bigram language model. We call it model. We tie it to the GPU and we call it M. Here's our optimizer. Notice that hasn't changed a bit, right? Literally, I've made the whole class consistent with this. All right. That's your parameters. You got your learning rate, got Atom over there, got your training process. You should be tired of seeing these 3 lines of code, right? You should hate them now. All right, so optimizer, lost, backward, and optimizer, they change the weights. Notice that we invoke M here. Notice that XB and YB are the product of get batch. What was get batch? The 2 sentences, one shift with 1 letter shifted to the right. You see that? So at least that should make sense to you now, right? So we start here, get the batch, X and Y, basically the sentence, and the same sentence shifted by 1. That goes into M. We do the training, we do the predictions, okay? That's the training process. And now to generate, we invoke, this just means that we have a starting token, which is actually integer 0. So we just start at integer 0. And then we invoke generate. We give it context, which is the index 0, just to give it a starting point. And then it just starts generating stuff. And that's basically the idea. Once you get gen text, notice we just invoke decode, and decode just changes the integers back to the letters. Okay? All right. So now we are ready to go back into this M, right? So M is the model. So that's instantiating bigram model. So that means we need to go to this one. Okay? And if you notice, this forward function is where everything is being put together, okay? So take a look over here. So we start with this thing called self. So I should say, you guys already know this. The superclass is nn.module, so we're inheriting that from PyTorch. We are going to instantiate these objects here, and then we're going to build the architecture. So notice we start with the initial embedding, right? This is going to be, we get n by 40. And now we need to embed it to n by 40 by 512, according to the graph that I have. Obviously here it's n by 256 by 384 because it's the different set of values. Once we do this, we also do something called the positional encoding, okay? Notice it's really just 1 line of code. So I'm skipping this part, but it's basically what we're using to encode the order of the words. What that means is we need to know that the cat is sleeping. Cat comes before sleeping. And this is where we record this information, okay? It's just 2 lines of code, okay? We give it the data that goes into positional encoding and produces position embedding. This produces the embedding. And notice that all that happens is that both of them get added together. Okay, that's it. And they'll have the same dimensions. So token embedding, positional embedding is basically, I'll refer back to the diagram just so that you guys are getting the picture. This box over here and this box over here. Okay, that's that part. So you've got token embedding, positional embedding, they get combined into one thing. So now that I have that, we've got, notice that that whole architecture is just these 3 lines of code right there. That is it. Because we're doing all the heavy lifting in the classes, okay? So notice the first one. We've got the X, right? The X is n by 40 by 512 at this point. Goes into this object called blocks. Okay? What comes, so that's going to be all these blocks. 1, 2, 3, 4, 5, 6, until the decoder, all the 6 decoder layers. Okay? Then the next part would be a final linear layer. That's this one. So you ask yourself, so what is this in the middle? This LNF? Those are just normalization, they're normalizing the data. So as you have seen by now, a common thing in deep learning is to normalize the data. All right, so it's a normalization. LM head then is what gives you the last layer that produces the logits. Notice that when you say the logits, we mean B times T times vocab size. So that's going to be in the diagram n by 40 by 70,000 if the vocabulary is 70,000. In our example, it would be n by 256, right? By 65, because that's the number of letters that we have, 65. Got it? So this should be 65. So I can write that down in there, 65. For our particular example. All right, and then once we have the logits over here, basically we're doing the training, so we're going to calculate cross entropy and everything, right? So we've got ways of doing this computation. So we got reshaping of the logits. We'll come back to this, and then calculating the loss so that we can train the model. Okay, but let's just stick to the architecture because there's too many moving parts. So now we need to look how these were instantiated. In particular, I think the hardest one to visualize is blocks, okay? Because there are 6 decoder blocks in here. So let's go to the init function. Notice how simple and elegant this code is. So we've got the initial token embedding table, this one over here. So what happens is that Torch has this nice object called nn.embedding. And basically, it's almost like you can just use this to kind of tell it to create the embedding. Notice that what you do is you go from vocab size to n embedding. So what is it doing? Think about it. If we have a vocabulary of 70,000, right, and an embedding of 512, effectively, that tensor is of size 70,000 by 512. So for every one of the words in our vocabulary, we have a matching embedding of size 512. Do you guys see that? That's all you have to do. That's literally all you have to do to create embeddings. Okay? So you start like that. So n embedding is vocabulary size to whatever embedding size you want. So in our example, what would this be? 65 by 384. Do you see that? Okay, good. So that creates our first now n by 40 by 512 tensor, right, at this point. As I said, this part of the positional embedding, I'm kind of skipping for now, but just keep it, the thing to understand about it is that it's the same size. And so if we have n by 40 by 512, this is going to be the same size. and we encode another vector with position, and that is given to those two things are added together, as you can see over here. So I will come back to this because it requires like a whole very deep explanation to prove that it works, right? So for now, just kind of believe me that it'll do the job, okay? And it's a way of encoding position, but it's just this one line of code. All right, so we added them together, and now comes this part. Self blocks actually amazingly creates basically these six layers, okay? So how is it done? So we're gonna go over here. We need to look at blocks, and if you look, this is blocks, that line of code. So we have used NN sequential before, right? Do you guys remember that we've used it throughout the semester? And with NN sequential, it allows us to do what? Just put in CNN1, CNN2, CNN3, CNN4, and whatever we give it to the model, it'll go through them one at a time in sequence. You know what I'm saying, guys? Okay, so that's how you do it. So you just create a thing called blocks. You instantiate several of these things through NN sequential, and now once you give an input to blocks, it will go through all six one at a time, as we have done all semester. So the way to implement that is through this list over here. So once again, we have a list over here, okay? Notice we're just iterating this, the little underscore just means drop the index. So we don't have an index. So 4 in range n layer, we have 6 layers. So it instantiates 6 blocks. Do you guys see that? All right, it instantiates 6 blocks over here. We need to pass it this parameter n head because we're going to be using that inside the program, and we pass it the embedding as well. Okay, so we need to drill in to block also to define some things, but for now we've created the sequence of the 6 decoder blocks basically. Okay, all right, so then that's it. So by just doing this code, we've got our 6 of these. Now we just need to define this part over here. So that's going to be, as I said, there's a layer norm, LNF. Notice it's a layer norm. So we're just normalizing the data. And then finally over here, we've got LM head, which is NN linear. Okay. And that's the last part that goes from 512 to 70,000, or in our example, from 384 to 65. To produce the word that it's predicting, basically, the LM head. If you notice, that comes after the blocks over here and the normalization, and this produces literally your logits, which are the words that we are going to be using. Does that make sense, guys? So we've touched on all the architecture at a high level. So now what do we need to do? We need to start drilling down into these decoder layers, right? Individually. And then from there into the heads and so on. So let's go ahead and do that. So now I'm going to, basically the first object we instantiate is the blocks, right? So that should be what comes next, I believe. Yeah, block. So now we have each of these blocks, okay? All right, so we passed it n embeddings and n heads, right? So that's 6 heads. And the embedding size is 384, okay? So the first thing we do is calculate this metric over here, head size. So that's just a division of n embedding by n head. So I'll use the example that I have in my diagram. So in my diagram, I produce n by 40 by 512. However, in each block, I have an attention head. An attention head. The multi-head attention is going to be what Joey was trying to implement. So he was doing 6 heads. But the 6 heads, I believe, were independent. So they're in parallel. So what happens is, think of it this intuition. You give it an n by 40 by 512. You run it through 6 parallel matrix multiplications. And what do you get? An n by 40 by 512 multiplied by 6. So now, what do you do with those 6 things? The easiest thing is just to concatenate them. But then you have n by 40, and then 512 times 6 is some large number. Do you see that? And that's too big. So what did they do instead? What they did instead is that each of the heads gets n by 40 by 512, the exact same one, but it processes it into an n by 40 by 64. So it basically compresses it a little bit. And then they concatenate. So 64 times 512 is what? Should be, or 64 by 6, sorry. 64 by 6 should be 512. Hold on, can't do math right now.
4 times 6.
It's 64 times 6 or 8. Yeah, sorry, here I have it. So, sorry, I couldn't find it, so I was trying to work it out. So, basically, this operation is to divide the embedding by the number of heads. So, let's go to the example of the embedding of 512, right? So, I want to have 8 heads. So, 512 divided by 8 is 64. Okay? So, remember that number. Because that's important, because as I said, you get the input, it's going to go into these 8 heads, it's going to get processed, and the output is going to be n by 40 by 64, not n by 40 by 512. The reason being is you're going to concatenate them to make an n by 40 by 512. It's a trick that they did, once again, for GPU processing, okay? Also to constrain it a little bit, probably. Do you guys see that? So that's what this head size is. There's number of heads, there's embedding size, and then there's head size. So notice that now you have the multi-head attention with n heads of head size. This multi-head attention is going to be an object that's going to contain the 6 heads in parallel. Okay? So that is this SA, and then you have the feed forward at the end. Because remember that we are looking at this one, each decoder layer. We're no longer at the 6 layers. We're only in each of the decoder layers. Okay? So that's going to be multi-head followed by a fully connected layer. So, okay. Well, is that what we're doing? We take in X. Notice ln1 is a normalization, and it goes into self-SA. Do you see that? Self-SA is this one, which is a multi-head attention. So we got to go into that class to kind of figure out what it's doing. But I'm already telling you there's 8 or 6 parallel heads in there that do that trick that I just described. The output of multi-head attention, notice over here, is X, which goes into another normalization, ln2, and that just goes into FFW, which is nothing more than our feed forward. That should be pretty familiar to you. Okay, pretty familiar, totally. And then finally, you get an X. Now, you might ask yourself, what is this X plus X through a function? That is called a residual. This is actually, in my opinion, one of the most important discoveries in deep learning, because what effectively allows you to create very deep neural networks, to get rid of the vanishing gradients problem. You know, if you do 0.5 times 0.5, 0.25, right? Now do 0.25 times 0.25, something even smaller. Now that times itself even smaller. Eventually it's a 0. So that's a vanishing gradients. But if you do this little trick, solves it. And this is what allowed really deep neural networks. Okay? All right, so we've talked about the block that is made up of the multi-head and the feed forward. So now we got to drill down into, well, let's start with the feed forward. This should be super easy, right? So we got a sequential again, right? We get it the linear, ReLU, linear dropout. There you go. We invoke net, right, which is that. Notice that all it does is it takes the embedding layer, let's say 512, and then it makes 512 times 4. That's the next layer. Then 512 times 4 back to 512. Why does it do that? Give it a little bit more space to think. But you just want to have one final linear layer there, or a neural network layer there, the feed forward layer. Do you guys see that, how it's going through that? Okay, so this one should be simple, right? We're almost very close to the end. So then we just have 2 more classes left. So we instantiated multi-head, right? We instantiate multi-head here, which is SA. So let's take a look at what's happening in multi-head. If you look, it's right there. It's pretty obvious. We create a list. We once again, with a list comprehension, iterate 4i in range num heads, 6 or 8 heads. Let's stick with the example of 8 heads because I already did the math for that, right? So now I have 6 heads. Notice that this is not in NN sequential. That's important because that means it's not going from one head into the next head into the next head. Instead, it's just a list. So they are independent of each other. There are 8 parallel independent heads, and then you have this linear one. So notice what happens here is you instantiate then the list, right? So now, whereas here you created the 6 or 8 heads, here you invoke them. So you do for H in self heads, where self heads contains the 8 heads, let's say, right? Let's stick with that number. And then now you have a list here of 8 H on H with an X. You see how there's 8 of them independent of each other. And notice then you have a torch function called cat, which is concatenate. Why is that important? Because you're going to end up with 8 tensors that are n by 40 by, not 512, 64. You're going to concatenate them, right? And when you concatenate them on this dimension, right, what's going to happen? What comes out of it is n by 40 by 512. Effectively, you ran the input through 8 heads, it compressed them from 512 to 64, and then it takes the 8, and boom, it creates the tensor again. These are just the things in transformers that are just like very GPU required. You know, you just need to do these things. All right. And then once you have that, you just pass it to the next layer, a linear layer over here. You add some dropout, and that's it. So there's one thing that's left is what is a head, right? So we need to go to the final class, which is what is a head. Where is that? There it is. The head is actually where something very important is happening, which is the attention mechanism. This is where we pay attention to things, okay? The best way to think about this is you have an English sentence of 40 tokens, right? We're gonna then create a matrix that is 40 by 40, where we have all the words as rows and the same words as columns. And now the transformer needs to fill in those values. Once again, like the CNN, there were no values in there, but after it has trained, it learned that there's a relationship between certain words. For instance, the example of the bank of the river was very slippery versus the thieves broke into the bank and took all the money. You see how we have the same word bank, but we need to create an embedding of size 512 for one version of bank and another embedding of size 512 for the other bank. Do you see that? We can't have, if we had the same embedding for bank relating to river and bank related to bank, you don't have a good understanding of what you're reading. This is what gives power. Possibly, this is like the thing that gives it the most power to the transformer, because it pays attention to what it's seeing, and it's going to produce embeddings for bank that are different if it sees, because what's going to happen if it sees bank and river, there's going to be some activation there. Or if it sees bank and cash and stolen, there's some activation there. Do you guys see that? That's the intuition that I can give you about this, okay? So how is this accomplished? So this is basically where you have, so all of this code, which is probably the most difficult to comprehend as it's written here, I have it written out more in the mathy operations over here, okay? This is like the actual linear algebra multiplications, and you can see that it creates an n by 40 by 40, where it would be x times x, right? The only thing is they don't actually do that. Instead, they take, notice that they take an x over here, and then they take the same x over here. They multiply it times some weights plus a bias, and they create Q and K. And then Q and K are matrix multiplied over here to create that 40 by 40. The trick is you're not actually directly comparing x times x. Instead, x goes through a matrix multiplication or multiplied through times weights, and the x is multiplied times another set of weights to produce Q and K. And then Q is what is compared to K. The intuition there is probably you're giving it even more flexibility because you also have to learn those weights to produce the Q is from X, to produce the K is from X, but it's a different set of weights. So you don't directly compare the X's, you compare them through the Q times K. You guys see that? I know I'm running out of time, but this is the idea, the most important idea. So you create Q, K of the X's, you matrix multiply it, you do, which is here, you do some operations, but basically effectively you end up with your n by 40 by 40, and that's the attention, which I called in this code by the way, scores matrix. And then at the end, you create a V also from X, and that's what allows you to produce the n by 40 by 64, okay? This is linear algebra, standard stuff. I mean, you can manipulate the vector that you have just by creating the weight in the way that you want it, and you get that size, okay? So notice that I started with the x's, I did the attention, but not x to x, instead q to k, where q is just x times w plus b, but the neural net needs to learn these weights. So that's a good thing. Then we multiply it times v, and that produces n by 40 by 64. So we just have one last thing. Each head then produces an n by 40 by 64. So I need to concatenate these. And although I showed you, I want to show you the matrix multiplication. I think I have it here somewhere. Here it is. So the input, imagine, is that one, decoder layer, right? Notice that it's the same input for every one of these. I have C1 all the way to C8, right? And every single one is input, decoder layer, input, decoder layer, input, decoder layer. So it's the same input to all 8 of these heads, okay? Remember, this is just me like breaking it up into the math, the underlying math. I already showed you the code. And then once you have these 8, then they get, that's these 8 over here, which get concatenated. Each one of those was n by 40 by 64, but after concatenating them, you create a tensor of n by 40 by 512 because we established that 8 times 64 is 512. And then once you do that, that's it. You just, once again, multiply times some weights times some biases. You do it here, right? C concat times W's. And then notice that basically creates C1. And then I guess I used the same variable, but it should be okay. C1, and that goes input, the original input plus C1 to create yet another residual. That's kind of it. So I kind of made it with 2 minutes. I know it's a lot. I never said transformers were easy. This is only the GPT, which is only the decoder. But They're definitely hard. But if you want to know how ChatGPT works, what I can tell you is this, and this is true. This is the exact architecture of ChatGPT. To generate what they call the GPT-3, GPT 3.5, or the GPT-4. Remember that GPT 3.5 or GPT-4 is not ChatGPT, right? They start with GPT 3. I think they're up to GPT-4 now. And from that's what this gives GPT-4. So the architecture is the same. So then you might ask, why am I not a billionaire, right? If I know this, because while I have the architecture, the software, I don't have 10,000 GPUs. I don't have all the data in the internet and all the books in the world. And I don't have a cloud that I would have to pay like $1 million or $2 million to train for 3 months. That's what we don't have. But we have the architecture, and this does not change. They might do little tweaks here and there, but in general, this is it. So I encourage you guys, this will conclude the lecture. Hopefully I wasn't going too fast, but I was trying to get it through the time. Run the code, look at the matrix multiplications, which is like the underlying math. So just to give you an idea, whenever you see something like linear, right? So where's something that's like linear? Yeah, this one. This linear here that you guys just write NN linear and that's it. It used to be basically that you would linear didn't exist. So then you always had to do such a thing like this. You initialize the weights, you initialize the biases, then you had the familiar function matmul, and you had to multiply x times w plus b, and then you would get q or whatever. This is what every linear is. Okay. Well, not in this case, query key and value is the attention specifically. I'm just saying linear is just the matmul operation of multiplying x times w plus b. That's all I mean. Attention requires these three operations in the code that I described to you here. So unfortunately, I don't have more time to drill down on this. But this, yeah, this QKV, matmul QK, that creates the score, the attention. That's the 40 by 40 matrix. Just remember, not x to x, but instead k to q, where k to q is from x, but multiplies times a set of weights that must be learned. All right? All right, I will stop the video here. That concludes our discussion. Hopefully, I mean, I wish I had more time, but I just don't.